Hadron Collider session with Thiago, who is local. Guys, so thank you so much for attending the workshop. So take your time.
My pleasure. So you can hear me well, right?
Yes.
Okay, so good morning, everybody. My name is Thiago Tomei. I'm a researcher here at the Center for Scientific Computing at UNESP in the bottom floor. And I also teach here at the Institute for Theoretical Physics. I'm a member of the CMS collaboration since 2006. And in the run-through of the LHC, I have been involved on the search for dark matter at CMS, which is what I'm going to talk to you about today. All of you probably know dark matter better than me, but I am contractually obliged to talk about it in these terms, okay? So, you all know that there is a lot of gravitational evidence for dark matter in all, let's call large scales, okay? From the rotation curves of galaxies, to lensing, to the infamous bullet clusters, to large-scale structure evolution, although this is a simulation from these guys here, but the point is that if you don't have the right mixture of dark matter, you cannot, when you evolve the universe, you cannot see the kind of large structures that we expect. So, it is fair enough to say that dark matter exists. Fine. However, what dark matter is a completely different problem. We are more or less sure of what is not. I'm not going to show the pie chart here, okay? But I'm going to talk about something that Profumo calls, for instance, the gross features of dark matter. What do we know that dark matter cannot be? First, dark matter cannot shine. It has to be dark. Usually, this means that if it is a particle, we want it to be electrically neutral. And also, there are some limits on the dipole moments, both magnetic and electric. But, and everything here has caveats, okay? Because there are ways to escape this if you assume that dark matter is milli-charged, micro-charged, stuff like that. It has to be collisionless. What does it mean? It doesn't interact with normal matter, fine, but there are also limits on how much it can interact with itself, which translates into these limits of sigma chi over its mass. In broad terms, there are no dark planets. There are no planets of dark matter lying around just waiting to be found. It has to be classical. It has to be confined in kiloparsec scales because of what we have just seen here. So this translates to limits on the de Broglie wavelength, and this in terms translates on limits on its mass. And then again, depending on its spin. It has to be fluid. It cannot be some super heavy macroscopic-like particles with masses, millions of sun masses. Or else some calculations on the stability of bound systems go awry. And then this, of course, translates into limits on its mass in electron volts. And it has to be stable or long-lived because it has to be around here, around the universe right now. It cannot have been decayed. The point is that these gross features here, they can be translated into this diagram here, which has a much larger range than what we are accustomed to. And bottom line, we know almost nothing. And then depending on the kind of model that you want to work with, you are in different regions of this diagram. Q balls, the infamous WIMPs, axions, something called fuzzy cold dark matter, black hole remnants here in this corner. Now, all of you know, this is a gigantic field. I obviously won't have enough time to cover 1% of this, so I'm going to focus, as you can expect, in WIMPs. But the WIMP paradigm may starting to come under fire with the latest results. We'll see about that. Okay, so We know that dark matter exists thanks to its gravitational effects. But that doesn't help us much. How do we actually see it in some other way? And this, again, is something that you're probably tired of seeing. We either detect it directly, so you make these big tanks of xenon or of something else, doesn't matter, and well, it matters, of course, but the point is that you make a big target, and you try to detect when a dark matter particle scatters from the nuclei of the material. And in some particular cases, xenon, the xenon experiment has also done it in 1 or 2 papers. You can also get it through recoil with the electron. And then you search for this signal. You can search for it through indirect detection. So in gross terms, you expected the dark matter to annihilate with itself. And remember, it has very low, because of the fact that it's collisionless, this is very, very tiny as well. And then you expect some effects on particle distribution. This can either be things like AMS, so you put a telescope in the sky and search for excesses of antimatter, for instance, or you can use the matter-antimatter equilibrium in the early universe, and then you search in the data of Planck or things like that, and try to see deviations. And these are completely different experiments that have their own merits and flaws. And then there's a third direction here. We try to produce it in the lab. So you scatter standard model particles and get dark matter out of it. This is completely complementary to direct and indirect detection. And this is what we do at the LHC. We try to collide protons and hope that dark matter comes out of it. And there is a very rich phenomenology that goes with it. And why is that? Because remember, dark matter is dark. So it doesn't interact with our detectors. So how do we plan on actually measuring the presence of this thing? I'll talk about that. But first, let me quickly flash, and this was the best I could find. If some of you know that these plots are already obsolete, please raise your hand now. These, for instance, the stats of direct detection of dark matter, okay? So these are the latest xenon one-ton results, which for high masses of WIMP are the best in game, as far as I know. And then for low masses of dark matter, all the way to 0.6 GeV, you have a plethora of other different experiments. Dark side, this dotted line here, I think it's Lux, which starts being a bit competitive here. And this is for spin-independent interaction, which in terms of what I do, it means vector or scalar dark matter, or thermal dark matter. But it doesn't mean any interaction of dark matter with matter that has a gamma 5. We'll see spin-dependent results later. Most of you, all of you know also that there is one problem with this kind of experiment, is that the sensitivity is going lower and lower, which means that soon we'll hit something which is the dreaded neutrino floor, which is we'll start having to take into account the background of neutrino interactions with our big target of xenon. Right now, the experiments are essentially background free. When we get the neutrino background, and as far as I know, there is no way to not get the neutrino background because you cannot shield against the neutrinos. It has to become a different kind of experiment. No idea what's going to be done at that point, okay? I'm a
Maybe we see that matter.
No, sure, yes, of course. Then somebody goes to Stockholm and collects their prize, fine, but I'm never an optimistic in my life. No, no, it's too much fun. Now, if you want to search for dark matter in collider, you need some kind of model, some kind of guidance. And this is the slide that everybody steals from Team Tate, which shows us the parameter space, quote unquote, of how good is our guide. So on one side, we have effective field theories, which you can parameterize like contact interactions, dipole interactions. And here you have full-fledged complete models, ultraviolet complete, all the bells and whistles. SUSY is obviously here, but also stuff like the little Higgs and the universal extra dimensions. So this is one kind of search that is done at the CMS, at LHC in general. But the point is that most of the time, these kinds of models have too much parameters, and the search have to be tuned for it. On the other hand, if you go with effective field theories, then you have almost no parameters to tune, and this is what we were doing at the LHC for run 1. But the problem is it has been shown that at LHC energies, effective field theories are not quite the correct description to do this kind of search. So we cooked, and we, the community, cooked something in between, which is the simplified models, which are not complete models, but they are models that have mediators and are a bit more realistic than these crude field theories. And the simplified models were what's going to be used for the LHC run 2 search. There is something else here, which is simplified models which have a reasonable completion to ultraviolet, but unfortunately I didn't find the slide that I wanted to steal that had the extra thing. Now, what does this mean in practice? This means that you have these kinds of diagrams here, and you search for these kinds of processes at the LHC. Usually you want to produce a pair of dark matter particles. And why do you want to produce a pair? Because you assume that there is some kind of symmetry, doesn't matter what, can be Z2 symmetry or something like that, that are parity in case of SUSY, that dark matter can only be produced in pairs, and it's usually the symmetry that protects dark matter from decaying into something else. At the LHC energies, you have to put a mediator to produce the dark matter. So here, for instance, you have a Z prime. Here you have a scalar. Usually, but sometimes you can even say it's the Higgs here. You have your choice on the spin of the dark matter, on the spin of the mediator, on the couplings. Usually parameterize these kinds of productions by these 4 parameters, mass and, counting with the spin, of course. But given a spin for the mediator and for the dark matter, you parameterize with the mass of the dark matter, the mass of the mediator, and the couplings. Now, what's the problem? Remember, dark matter is dark. It doesn't interact. So this means that this chi-chi pair here will not be detected in my detector. So I have a problem. How do I see this? And we all, again, know the answer. You need this production here to recoil against something, leaving some transverse momentum imbalance. Assuming the detector is minimally good and well built and the people running it know what they're doing, we hope that transverse momentum in the detector should balance. If you see an imbalance, that means that something left the detector undetected. Usually, go ahead.
Excuse me, are you excluding from your circle, let's say the WIMPs, for instance, supersymmetry, neutralinos?
You can cast WIMPs, supersymmetry, neutralinos. Actually, these are WIMPs. Supersymmetry, neutralinos. You can make explicit search for supersymmetric models in this corner here. But then the point becomes that it's not a generic search for dark matter. It's a search for supersymmetry. So you're absolutely right. We can and we should cast results for SUSY into results for search for dark matter. Unfortunately, sometimes we don't do that. There is another question there? So yes, he's absolutely right. There are also SUSY searches that should be cast in terms of dark matter search. sometimes it's done, sometimes it's not, obviously for reasons of personal power, but we try when we can. And then you have to recoil against something. And the fun of the story is, what is this something? Sure, it's easy to say, oh, I'm just going to recoil against initial state radiation, but there is much more that can be done. The point is that it can be anything, and when you recoil against this X object, you call it a mono-X search. But then, you have a whole other way of doing this job. You can search for the cascade decays, like SUSY, where you start with whatever superparticle, and then it keeps decaying, but the R parity has to be conserved, so eventually you get the neutralino in the end, plus a lot of other particles. Fine. You can do searches with long-lived particles. I'm not going to talk about it, but we can talk about it in the discussion. And remember, if this mediator here is produced by dark matter particles, it can also decay into dark matter particles. That means that it can also decay into standard model particles. So you can take all your searches from DiJet search, all your results from DiJet searches, from dilepton searches, and recast them into search for dark matter, assuming that the mediator that you're searching for is the mediator of the dark matter of the dark matter sector. Again, this is, as you know, this is a whole world, and I'm just going to chart a little part of it. Luckily, there are people that are specialists on helping us chart this world. So there is this LHCC dark matter working group. These guys produce guidelines and recommendations for these benchmark models.
What is the second C?
LHC Center. Yes. They are. And they produce guidelines and recommendations for benchmark models. They help us cast our results in ways that can be compared directly with the direct and indirect detection models. They were the ones who came out with this idea of making the dark matter limits from mediator searches. And now they're working on some kind of model evolution. So more interesting models where the mediator is spin 0, T-channel production, stuff like that. So if you download the slides and click here, you go to the website. Now, we want to search for those diagrams. Fine. We want to search for these processes. We are the LHC. Just take the data and do it. Again, I'm contractually obliged to show these next two slides. You know what the LHC is. It's the most powerful collider in the world. It has been given us an amazing amount of data, has the 4 experiments, 100 inverse femtobarn of PP collisions. You can see here run 1. Here, more or less in the middle, is the discovery of the Higgs boson. And look at how much more data we took after that. And it's also used for heavy ion studies as well, which is something completely different. I particularly work in the compact muon solenoid. It's an hermetic detector, so it goes to pseudo rapidities all the way to 5.2, and there are upgrades coming to make it even better. It has system for tracking charged particles, measuring the energy of electromagnetic interacting particles, measuring energy of hadrons, and measuring the momentum of muons. Hermetic means that if there is no, it's a 4-pi detector. If there is nothing that escapes the detector undetected, that means that we should see no imbalance. And that's the key to searching for dark matter. Assume again that the detector is well calibrated and people know what you're doing. And the point is that, and you're going to indulge me now for 5 minutes, because calibrating the detector and people knowing what they're doing is not an easy thing, okay? So this is what, if dark matter should be produced, this is what it should look like, okay? You should see a lot of energy going in one direction, and nothing, or almost nothing, in the other side to balance it. So here you have a big jet with 1.5 TeV, and more or less nothing on the other side, so it put this arrow to show. Notice that this is constructed like this, okay? The way you get the missing T, I know that all of you know it, but in case somebody doesn't, The way you construct the missing T is that you sum everything else and then take the vectorially and then take the minus sign. By construction, the missing T and everything else in the detector balance. What's the problem? The problem is not easy doing this, okay? A 13 TeV for run 2, and it's going to become even worse, we have a bloody problem here. Why? Because the detector is high luminosity. So that means that if you want to have all those 150 inverse femtobarn, we have to deal with simultaneous proton-proton interactions. And every year it gets worse. See, this first one, distribution here is 2015, with an average of 13 collisions every bunch crossing, then goes up to 27, 38, 37. And notice, only one of these collisions here is the important collision that I want to analyze. All the others are a bunch of junk. Not junk, but extra proton collisions that just happened around. And I have to clean all of these to isolate the one collision that I'm interested in, and then analyze that to see if there is an imbalance. And then, of course, I have to do statistics and see if there are enough of these to warrant the presence of dark matter. Tell me.
This is a silly question, but why did it become better from 2017 to 2014?
The machine guys found a way to make it better. I have no more details. You see here that the 2017, there is a bimodal distribution. See here, the way to have high luminosity for in 2017, it was this horrible situation here around 60, and then they found a different way to do it, and then we went back. But for 2018, we have the dark blue. Okay? And then you have to take this data. It's not that easy. So you have to trigger, you cannot save all the events that CMS takes. You have to choose some of them in quasi-real time, make an analysis in quasi-real time. Quasi-real time here means 2.4 microseconds to a level 1 decision, which is something that you do on hardware, and then something around 100 milliseconds to actually run the full analysis and check if you want to save the event or not. If you don't save the event, lost forever. And I'm already going late. But my point is that when you do this quick analysis, the missing ET, I'm going to just call it like that, missing ET, is not the same as you would expect in if you did a complete analysis. So if you ask for a missing ET online, let's focus here on dark blue, of 60, 80 GeV, it actually corresponds to 300 missing GeV, missing ET when you do the full analysis. And here, this is for the level 1 trigger, and this is for the high-level trigger, which is a more elaborate, but still has to be fast. So you have to take these things into account. And then you have to compare with what should be the real missing ET, because remember, the detector is not perfect. That is, the response of the detector, the resolution of the missing ET you measure, and you have to do a lot of cleaning. So see, here, these white dots here, red dots here, they are the missing ET that comes out of the detector. This is not SUSY, this is not dark matter, this is miscalibration, errors, holes, everything. When you do all the cleaning, you have these black points here that actually follow the distribution of the standard model backgrounds. You see Z plus jets, W plus jets, and top quark production. Okay? and we try, we have to develop techniques, and all of this becomes worse with PILAP, okay? So here I'm just flashing these that show, for instance, the Jacobian peak of the W with some regular missing ET, and we do a better treatment to get rid of the pileup. Okay, so now that hopefully I have convinced you that this is hard, we go here for the searches themselves. This is a canonical search, okay? You have dark matter recoiling against initial state radiation, dark matter plus jet. This jet here can be either a gluon from initial state radiation, or a WZ boson that decays hadronically. And you have these, what we call monojet and mono-V. I'm not going to read this, but the point is that you need missing T, you need the jet, and you need those two things to be aligned in such a way that they're recoiling back to each other, and in some angular configuration that you make sure that it's not mismeasurement. And then you have the standard model backgrounds and the data, and you do statistics to find out if you are seeing some deviation or not. But let's go into it a little bit deeper, okay?
What is the difference between red points and blue points?
This is a technicality. This is pre-fit and post-fit background measurements. This is the data over prediction, but what you change is the prediction because there is a fit involved.
There's a fit in the prediction.
Yes. Now,
And once you fit, everything is within one sigma.
yes, so bottom line, no dark matter. Then we have limits. Now, look at this.
But the fit is not dangerous.
The fit is what?
It's not dangerous. You cannot hide the signal in your fit.
We have, we do work to make sure that the fit is not dangerous. We have control regions, we take care. Now take a look at this, because here there are two regions, okay? For low missing ET, you see here that we have already tens of thousands of events. So this is all systematically limited, okay? There is no more statistics that can save us here. It's not just take more data. So you have to model the Z2 neutrino plus Z, the W neutrino plus Z, the top quark, very well to see if we can model this background here. And the more pileup you have, the harder it is. While here on the high PT, it's a different story. Here, you really have to take more data to keep filling up this distribution. And then you need to have these standard model predictions really well done. So right now, what we have is NLO full QCD plus electroweak, plus some corrections for special cases at NNLO. So it's not just a question of run it and take more data. And then you don't see anything, and then you cast back the results in different planes. So for instance, in the plane, you can fix the couplings and ask yourself, for which values of dark matter and mediator you have you have excluded. Or for which values of coupling and mediator mass, assuming a fixed ratio, you have excluded the presence of dark matter. So it's these two plots here. These are mediator versus dark matter mass. Or you can fix both couplings and cast into cross-section and dark matter mass. And then you have this kind of a plot here. But what's really interesting is when you actually go back all the way to the sigma dark matter nucleon, or sigma times V, and you can cast the CMS results here into this plane to compare with the direct and indirect detection experiments.
How do you go from the standard model cross-section to dark matter connected to dark matter nuclear cross-section?
You assume form factors and some other extra constraints.
There's model dependence in this.
There is a bit of model dependence, and that goes in as systematic uncertainty.
I think there is a lot of model dependence.
No, there is a lot of model dependency because you have to say if it's spin independent or spin dependent or. Yes, but given that you fix that, now you go and compare.
If you fix a model, there is no model.
But model is fixed. Model is fixed as that prime model, right? That prime mediator, right?
It's one of these, for instance, Z prime or scalar. You fix the model, and when you fix the model, but you still have to go from a quark-quark interaction to dark matter to something which is dark matter nucleon. And here there is form factors, extra uncertainties. But we take care of that.
Okay, I see the model there. Vector, mediator, Dirac, dark matter.
Exactly.
So there's some coupling constants. So everything you have to set to get this matching.
Yeah, but remember, we have quark-quark, and you have to go to dark matter nucleon. That's also that. The bottom line is that usually what we probe low mass dark matter because the direct detection experiments they lose sensitivity because they cannot see the recoil anymore, while the ones that are particularly well suited for low mass search they cannot reach us yet. While if we're doing something that has a gamma 5 on it, like pseudoscalar or axial mediator, then we are much better. And this is what I mean by the complementarity. I think this slide is important, so maybe you want more questions here.
So, yeah, so the dotted line, so this line, the dotted line is the CMS result, right?
On the dotted line is CMS expected, and red line is CMS observed. So the one that really is the limit is the red one.
So what is excluded in this plot is from CMS at 9.5?
Everything above and to the left. Just like in Xenon, everything above and...
If I can make also a comment, this is something I worked on and other people worked on. These two bounds are probably in the dark matter couplings at different scales. Okay, so the collider scale is very high energy to center of mass, but you're using the direct detection plane. So when you plot the lux, the xenon one-ton bound, you're fine. You're just copying what the collaboration is telling you. When you go to, you translate the LHC bound into this plane, you have to run the coupling. So in this case, so actually in the case in the middle, there is an effect which alters the bound by a factor of 2. So it's something substantial. But there are cases where these effects are really important and they change the bound by orders of magnitude because there are mixing induced who is running, and then you go from spin dependent to spin independent and so on. So this is another subtlety to keep into account, which is of course model dependent, but yes to be.
Yeah, but I agree with this, but since he has a vector current, well, this running is not that important.
For the one with the vector, yes. For the one with the axial, like,
But the axial vector makes a big difference, of course.
Yes. No.
That's what I'm saying, because we have been discussing this a lot, back and forth in the write-up of the briefing book.
In the what? Sorry?
In the briefing book. So there has been a lot of discussions, Katerina.
Of course.
Yeah. And so we agree finally to put a big caveat in every figure that says that it's very specific to this very specific model with the couplings that we have put there. So there is a lot of tension in the community about saying just plainly complementarity, because
Really, I always consider this as qualitative bounds who are very specific.
but it doesn't no.
Then
A
until
lot
you
of people
find
care a
something,
lot.
you
A lot of
can
people who are
give you an impression and say there is nothing there.
a lot of people who are looking and
You
saying.
may as well do it well.
Yeah, you can regard it
Sí,
whatever you
sean
want.
maleducados, por favor.
Exactly.
So what I want to say is that there is a lot of animosity in the community because, of course, you are looking at this very low dark matter and you're trying to make the complementarity, which for these models we are looking here, besides the fact that there is not the running of the couplings and therefore there is a lack of issue factor there. One is saying that colliders can really test for these particular cases low dark matter. Of course, there are a lot of experiments that are specifically targeted to look at low dark matter, and so those proponents are extremely careful about how one phrase what a collider can do. So I'm just saying that, it's good to say complementarity, it's good to say we are probing these areas, and one has to keep a grain of salt when one says colliders are so complementary in research.
One can simply use running, right?
But
And
it's
make
not
a
dependent thing.
But once you specify
But
the
in model
model, there is no
is-
model
Yeah,
dependent.
yeah, of
model
course.
is-
What I'm saying is that you are probing one given model. You
Yes.
are probing one given model.
Oh, Farinaldo.
Yeah, so just one thing. So let's say we have simplified models. So running is important, yes, but they are affected by UV completion of your model.
No, it's running between LHC scale and direct detection scale. This is because of different scales.
I know, but when we work on simplified models, we are not really trying to, we are trying just to
Doesn't
understand.
matter. You have a measurement at a scale, you want to connect another scale, you go from that scale to the other scale, regardless of the UV completion.
Yeah, for vector,
I agree,
vector
Sasha,
model
I
is
agree.
okay.
I agree
But
with you.
for a scalar model or axial vector model, it could be a big difference. So for this particular vector model is actually middle limits are quite precise, but one needs to say, as Marcel said, that we don't use or we do use running, whatever.
Okay, people, just one comment. We still have to go to the coffee break after this. So please, let's have the discussion, but later.
Okay, let's thank the speaker.
By the way,
again.
there is a question there, but I'll take it at the end, okay? I have seen it
Let's
already.
thank the speaker again. In the afternoon? Yeah, fine. So
And then this is the thing that I said that actually this is why I don't quit even though I am a pessimist. Because again, this is a lot of fun. Because then you open Pandora's box, okay? Not this one that we just opened, the other. We have dark matter with monophoton, mono Z2LL, mono top, mono double top. I mean, come on, this is epic. And then you go back and you do... Sure, this one?
Okay, so look, you should be pessimistic because all your results are within one sigma. So it's amazing that you managed to do that. So it's statistically improbable. Yes, so you probably are not allowed to show 2 sigma deviation. You know, I know cases of searches that they are not accepted because they show 2 sigma deviation. It's totally crazy.
2 words for you, diphoton 750. Exactly. 2 words for you, diphoton 750. Now, going back...
Change the community.
For your own sake.
People, please. Okay, let's finish this, please. So, you have all the summary plots, and with all the caveats that we have just quickly discussed, okay? Now, you can also do... Você quer que eu corte agora ou... Okay, 2 minutes, okay? You can also do dark matter with Higgs boson, and again, here you have all the decays of the Higgs boson, and the same story, okay? For low masses, assuming all these caveats, we can go to this different regime. I just really quickly want to show something else that is not exactly what we usually do. You can do dark matter in non-prompt jets, and this is one of the examples that I find nice that you have. And here it's fuzzy-like, see? So you have the gluino, which decays, I think this is the gravitino, right? Plus a gluon. And the thing is that the gluino actually flies. So you have this kind of thing, where you have a jet that's not coming from the interaction region, and the mu CET that's sort of kind of screwed up here because it will also not point. Notice that there is all of this, fine, but look at the backgrounds here. There is no standard model. The backgrounds are cosmics, satellite interactions in the LHC, and beam halo. It's a pain to actually manage to model this. And then you go and interpret it in terms of one model, GMSB. But we could do it in simplified model. Volunteers talk to me. And then you also have, no, I really have to finish, sorry. And you have full run-through results here with MIS-MPT plus Z gamma. And here really one of the mediator is the Higgs. Notice that this is a search for a dark photon of sorts and not of dark matter, but the signature is the same. So I'm just flashing the result here, and you have, it's a missing PT, right? So you should cast this into a dark matter search. And finally, you have leptoquarks, which is a half of run-2, that instead of having a simplified model, you have a more complete, I don't know if this thing is UV complete model, and then again you go and put limits on the mass of the leptoquark, mass of the dark matter search. Bottom line, searching for dark matter is our next goal. We have the LHC Center Dark Matter Working Group, which gives us guidelines and recommendations, plus all this discussion here that I'm going to bring home. And we are going to do all the analysis of the run-through data, which is well underway. So I have just flashed 3 results of the full run-through data. But for ICHEP 2020, stay tuned. Thank you very much.
Nicely done. So.
Oh, and that's the future here, eh? Don't forget it.
Okay, I have a really very, very naive question. So I have seen your plots when you have some slides before that, doesn't matter. So you were assuming a messenger vector, a dark matter fermion, or messenger whatever. No? So different possibilities. And then you have presented the expected bound and the observed bound. So theorists are used to also to see theoretical predictions since you are fixing the model, aren't you?
So we fixed the model, and stuff like alpha S running, PDF of the proton, whatever, goes as systematic uncertainties. There was also discussion in the statistics community of the CMS and also Atlas, I think, of some uncertainties related to the model itself should go as an uncertainty on the theoretical prediction. And when you do this kind of line where you have the Brazilian band plus the cross-section, it's easy to do. But when you have this plane and you carve out a region of the plane, it's a bit more complicated, and we're still trying to find out how to do that.
Okay, so.
Fernando, vê quem que é o próximo.
Okay. So Carlos, you last.
Yeah, also there was this guy behind that also wanted to ask a question.
I just wanted to comment and ask. So, in principle, the interpretation of LHC searches against different models, etc., well, one can done by phenomenologists, right? So, and the main requirement from you guys is to have your results very easy, accessible, and actually usable for phenomenologists. What is done in this direction, actually? Well, kind of.
What we should be doing is giving you guys the full likelihood. The minimal things we should be doing is to give at least a table of efficiencies and stuff like that. Unfortunately, we try, but the main goal is to get the result out, and sometimes the person power doesn't stay. We are trying, believe me, we are really trying. Just putting all the data in HAP data has already been a big fight.
Hi. So in the bounds that you showed comparing the cross-section with nucleon, it's just a stupid question. Why do you have the CMS, it goes back like that? Do you have, like, it seems that if for high cross-section you are not excluding the...
For high cross-sections we are not excluding...
Yeah, can you...
Yeah, I know what you mean.
You can show it, it goes like that.
Yeah, but I lost the...
So for the same... For the same dark matter mass,
This
you have
one?
2
No.
points, which is a bit confusing.
Like, I'm going to go there. This, here. Why? Oh, no, porra. Why does it turn back to the left there?
Yeah, for 2 dark matter mass, you have 2 points. So it's like, it seems that for large cross-section, you're not excluding. What's the meaning of that?
For large cross-sections, you do not exclude. No, it's not that. It's... yeah, I know. I think I know what it is, but don't hold my feet to the fire. I think this is related to the fact that if there is dark matter in that region, so high dark matter mass and high cross-section, then it starts also showing up in the control regions. And when we do the fit in the control regions doesn't work if there is dark matter there. I think it's that, but I could search more later.
Other reason. If the cross-section is extremely high, the dark matter simply does not reach the detector through the 1 kilometer of the rock.
But this is CMS.
Yeah, this is CMS. This is the CMS result.
But this is the interpretation from sigma. Yeah, it's interpretation.
No, but CMS.
Do you have the bound in the mass, mediator mass, dark matter plane?
They have all the bounds there. They're all
The
there.
other plot. I think it's clear from there.
I should have. You mean
Plot where you have dark matter mass and mediator mass.
like this?
Yes. So you see that for a given dark matter mass, there are 2 mediator mass, the bound, the line of the bound. So that corresponds to the 2 values of the first.
There is also the fact that if the dark matter is more than half of the mediator mass, then it also doesn't work, right?
Yeah, so just one thing. So the curve, yes, has to do with that. So the scattering cross section is also determined by the mediator mass, and eventually, when the mediator is heavier than the dark matter, then you won't see the missing.
No, and the
energy.
dark matter is heavier than the mediator.
You won't see the
yeah.
missing energy signal. So
Yes.
that's why it goes up.
You will never find anything. So look at your plots. So no matter how crazy the spectrum is, the observed follows within 1 sigma.
See, I choose to reinterpret that statement on I have plenty of work to do until I retire. See, I'm now optimistic.
Okay, so let's finish. Let's thank the speaker and finish now because we go for coffee break. Okay, just outside.
Good job. Very good. I didn't know that you.